Hi everyone. So first I just want to thank you all for joining me, and I hope that everybody's doing well during this kind of strange time that we find ourselves living in, right? So today we're going to review and discuss a little bit more about determinants of matrices. We've already encountered determinants in this course. Specifically, we've seen how to compute the determinant of a 2 by 2 matrix ABCD. And namely, this is AD minus BC. And we've seen this in the context of a matrix inverse. How do we compute the inverse of a matrix ABCD? It's simply 1 divided by its determinant. If this is the matrix A, of course, right? If that's our matrix A, then it's 1 divided by the determinant of A times this funny matrix dA negative B negative C here. We've also seen how to compute determinants of 3 by 3 matrices in the context of cross products. So let's just review cross products. Remember, in cross products we had the first row were those vectors I, J, and K. But what happens if we have just numbers? So let's try to compute in the same exact way. Nothing's different here. The determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's remember how we worked this whenever we were doing cross products. We took 1, the number 1, and we multiplied by the determinant of the matrix that was left over, right? The determinant of the matrix that was left over. Once you cross off its column and cross off its row. So times the determinant of the matrix 5, 6, 8, 9. And now we subtract, and it's minus 2 times the determinant. Cross off the column, cross off the row, and it's the determinant of the matrix that is left over, 4, 6, 7, 9. These matrices are called minors. Plus 3 times the determinant of, cross off the column, cross off the row, we have 4, 5, 7, 8. And now, because we know the determinants of all of these 2 by 2 matrices, we're in business for computing the determinant of this 3 by 3. This process is called cofactor expansion. Cofactor expansion. But I know what you're thinking. You're saying, boy, gee, howdy, what if expanding along the first row wasn't optimal, right? What if this isn't the best course of action for us? How would we expand about different rows? Well, let's see. Let's compute this determinant first, and let's try it another way. All right, so let's get a baseline. This determinant, this determinant is going to be 1 times 45 minus 48 minus 2 times 36 minus 42 plus 3 times 32 minus 35. I hope. We'll see. And so whenever we simplify, 45 minus 48 is negative 3, minus 2 times negative 6, plus 3, that's a 6, plus 3 times 32 minus 35 is again negative 3. So all of this together is negative 3 plus 12 minus 9. That's 0, isn't it? That's kind of interesting. So what do we know about this matrix? We've already talked about this. Because the determinant is 0, this matrix is not invertible. So if you were to augment it with a 3 by 3 identity matrix, you would not be able to find an inverse because there won't be a pivot in every row or what have you. All right, so let's try to do this another way. For our matrices, there's going to be kind of an invisible companion matrix that wanders around with them whenever we do our cofactor expansion. And it's just a matrix of alternating pluses and minuses. and this is true no matter how large the matrices get. This is going to be, this gives us the signs in our cofactor expansion. This gives us the signs in the cofactor expansion. So remember, whenever we expanded along the first row, like we just did in our previous example, the signs were +1, -2, +3. But let's compute the determinant of the same matrix another way. We'll compute the determinant of the same matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's an 8. And instead of going across the first row, let's do something really kind of fun and go down the second column. Let's go down the second column. And let's see how it's going to go. Well, the first entry that I see is a 2, and its corresponding sign is a minus. So it's -2 times the determinant. Block off the column, block off the row. We have 4, 6, 7, 9. The next sign that we see going down is a plus sign. So it's +5 times the determinant. Block off the row, block off the column. We get 1, 3, 7, 9. And -8 times the determinant of 1, 3, 4, 6. That's not so bad. And what do you get whenever you compute these determinants now? I see -2 times 36 minus 42 again, +5 times 9 minus 21, minus 8 times 6 minus 12. Well, what's this going to be? -2 times -6 is 12, plus 5 times 9 minus 21 is -12, minus 8 times 6 minus 12 is -6, and if we keep computing, we see it's 12, minus 60 plus 48, which is again 0. That's kind of interesting. So you get the same exact answer. And this is always true. Cofactor expansion doesn't depend upon which row along which you expand or down which column you expand. As long as you keep these signs correct, you'll always get consistent results, and that's kind of interesting here. In this case, this matrix is pretty not fun. There are no zeros, right? But I know what you're thinking. If these coefficients were 0, that would make my life a lot easier, wouldn't it? So let's see when we can exploit this structure. Let me switch pens. Let's do an example. Let's compute the determinant of a 4x4 matrix. 5, -7, 2, 2. 0, 3, 0, -4. Sorry, let me line everything up. -5, -8, 0, 3, 0, 5, 0, -6. You have all the tools to compute the determinant of this matrix. Give it a shot. Pause the video, see if you can do it. Alright, so we're going to exploit the structure of this matrix in our first go at this. I see that I see a lot of zeros in this third column, so I'm going to do cofactor expansion down the third column, and this is how I will expand this matrix. And remember, what's my... we're dreaming here, right? I know that I'm going to have a matrix with plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus, right? And as long as I remember this matrix, I will never go wrong and I'll get the signs correct. All right, so this 2 starts positive and I alternate signs going down this column. So I know that the determinant will be equal to +2 times the determinant. block off the column, block off the rows, and I have 0, 3, -4, -5, -8, 3, 0, 5, -6. How do we want to proceed from here? Well, I see a lot of zeros again, don't I? Let's go down the first column here. It doesn't matter, right? You always get the same. You don't have to be consistent between steps. So let's go down the first column in this next step. So we get +2 times, and now let's compute the determinant of this matrix here. This is a bracket, not another matrix, but whatever. We get 0 times the determinant of the matrix -8, 3, 5, -6. Hope you see where this is going. Minus, so +5, so minus -5 is +5, times the determinant of the matrix 3, -4. Ooh, I'm off the screen here. Sorry about that. Let me wrap around. +5 times the determinant of 3, -4, 5, -6. Right? And then plus zeros times some other determinant. Yeah? I'll get pretty nasty there. So what's really nice about this is that these zero coefficients kill everything. Yeah? Just like in this first step here, all of these other zeros made this the only thing that we needed to compute. So really, the only thing that we need to compute is 2 times 5 times -18 plus 20. And I think that's 20. There you go. I think that's 20. Could we go down a different column, or could we go across a row? Yeah, sure. Let's do it. Let's do that just for fun. Hopefully I won't get as messy. Let me rewrite my matrix down for a new piece of paper. Let's do one more way of computing the determinant of our matrix 5, -7, 2, 2, 0, 3, 0, -4, -5, -8, 0, 3. 0, 5, 0, -6. All right, let's do this again. Let's go down the first column this time. Let's go down the first column. Again, if you want to pause the video, give it a shot yourself, that's always good practice. So I see that all that I need to compute here is 5 times the determinant of 3, 0, -4, -8, 0, 3, 5, 0, -6. This is positive, negative, positive, so I get -5 times the matrix -7, 2, 2, 3, 0, -4, 5, 0, -6. And that's kind of nice. Why? Because in the cofactor expansion of this matrix, if I go down the second column, I have all of my coefficients will be 0, so there's no work to be done. So all that I need to do is cofactor expansion on this matrix here. And for this one, I'm going to go down the second column. Down the second column looks nicest to me. But does it matter which one you do? Nah, it's the same. So we get -5 times 2 times the determinant. Sorry, -2. Because it's in the second position here, so that's a minus sign. So -2, determinant of 3, -4, 5, -6. And let's compute this. We get 10 times -18 plus 20 is going to be 2, which is 20. Cool, so it works. That's kind of nifty, isn't it? I hope it's nifty anyway. I think it's cool. Okay. So let's do some special cases. what have we noticed if a matrix, a square matrix, right, for this cofactor expansion to work, we always have to go down to 2 by 2s, right? So it has to be square. So if a matrix A has a row or column of zeros. Well, if it has a row or columns of zeros, then we can just expand along that row or column, right? Doing that, what's the determinant of A? It's always 0. So if ever you see a row or column of zeros, you're done. The determinant's 0. And what do we know about this matrix? We know that it's not invertible, right? As an example, what if we wanted to compute the determinant of a diagonal matrix, A11, A22, ANN, with all the other entries 0? What's the determinant of an n by n matrix, where we only have diagonal elements and zeros elsewhere? Well, let's do a few steps and you'll see the pattern. This is going to be A11 times the determinant of, block off the row, block off the column. The only things that are left are A22, ANN, with zeros elsewhere. And there are no other entries in this term in the cofactor expansion because all the other coefficients are 0 going down this column. Well, doing the same thing, what's going to happen whenever we compute the determinant here? You'll have A11 times A22 times the next diagonal matrix, and on you nest. What's going to happen in the last step? We'll have A11 times A22. Oh, here's my cat. All the way down. we stop n minus 2, n minus 2. But what's left over? What's the matrix at the very end of this game here? Times the determinant. A n minus 1, n minus 1, 0, 0, a n, n. And how do we compute the determinant of this matrix? It's just the product again. So what's the product? What's the punchline here, guys? What's the product of a diagonal matrix? It's just the product of the diagonal entries. It's A11, A22, all the way down to ANN. And that's kind of nice. Let's do another example. Pause the video and think about the following question, or the example. Compute the determinant of A transpose. In terms of the determinant of A, what's the relationship between the determinant of A transpose and the determinant of a matrix A? They're the same, right? Because what's the relationship between A and A transpose? We just swapped the rows and the columns. We've interchanged them. So computing the cofactor expansion of A along any row is exactly the same computation as computing the cofactor expansion of A transpose down any column. And that's kind of nice. Let's think about another example. What if we have a diagonal matrix? Suppose A is equal to a diagonal matrix, A11, A22, all the way down to ANN. Here is my cat's tail. She's being a bad cat. And she's laying on all of my things here. How do we compute the determinant of this matrix? Okay, so hopefully this works. I'll get my cat off the desk. So how do we compute the determinant of a diagonal matrix? Well, let's do the same idea. If we expand down the first column, we're going to see A11. All the other coefficients are 0, and then we'll take the determinant of the next upper triangular matrix. So maybe I misspoke. This is an upper triangular matrix. This is an upper triangular matrix because all of the non-zero entries are above the diagonal. Only zeros exist below the diagonal. We call that upper triangular. And if I expand down the first column, then I have A11 times the determinant of this next upper triangular matrix. Expand down the first column, and we see quickly that this is again the product of the diagonal entries. And that's kind of nice. So the determinant of diagonal matrices and the determinant of upper triangular or lower triangular matrix by the transpose are both the product of the diagonal entries, and that's super nice. All right, let's talk about a theorem. This is super nice. Suppose we have two matrices, A and B, are n by n matrices. Then the determinant of A times B. So if you compute the determinant of the product, then it's the product of the determinants. Sadly, this is not true for addition. But if we have if we want to compute the determinant of A times B, then that's just the determinant of A times the determinant of B. As a quick example, compute the determinant of A inverse. Suppose a matrix is invertible. How do you compute the determinant of A inverse? Pause the video, try to figure it out. So first we need to note that the identity matrix is A times A inverse. And all that we need to do now is take the determinant of both sides of this equation. So we know that the determinant of I, what's the determinant of any identity matrix, is 1, right? Because it's the product, it's a diagonal matrix, only with 1s on the diagonal. The product of all the 1s is 1. And this is going to be equal to the determinant of A times A inverse, which is equal to the determinant of A times the determinant of A inverse. And we're done, because now we can solve for what we're looking for. So what's the determinant of A inverse? It's just 1 divided by the determinant of A, and that's kind of nice. All right, let's do some more examples. Example, let A be an n by n matrix. And I know how much you love true or false tests, or in questions on tests, so let's do a true-false question. True or false? Oops, true or false? The determinant of negative A transpose is equal to negative determinant of A. Pause the video, try to figure this problem out for yourself. So the first trick is to write negative A transpose as negative identity matrix times A transpose. Where, what do I mean by the negative identity matrix? Negative I is, well, it's negative I, right? It's 1s on the diagonal, but it's not 1s anymore, it's negative 1s, right? And 0 elsewhere. And this is certainly true. And so now, how can we use the property that we just found? We know that the determinant of negative A transpose is equal to the determinant of negative identity matrix times the determinant of A. So, what's the determinant of negative identity matrix? Well, what happens if I multiply 1 by itself n times? Oops, I can just write it here. It's actually negative 1 to the nth power, isn't it? Which is not always negative 1. So this is only true if n is odd. It's only true if you have an odd dimension matrix, which is kind of interesting. All right, let's talk about something else. Let's do a theorem. Let's talk about a theorem. Let A be a square matrix. One. If a multiple of one row of A is added to another row to produce some matrix B, then the determinant of B, the new matrix, is equal to the determinant of the original matrix A. That's kind of cool. 2. And I know what you're thinking. Who cares? What are we doing? 2. If two rows are interchanged to produce a matrix B, then we have the determinant of B equals to the negative of the determinant of A. 3. If one row is multiplied by k, some number k, to produce B, then the determinant of B is equal to k times the determinant of A. And this is kind of nice. It's nice because what's going on here? If you take a multiple of a row and add it to another one, that's a row operation, right? If we swap two rows, that's a row operation. This one's not quite a row operation, but we can just multiply for free, right? We can just multiply a row for free and leave it there. And so it's telling you how to compute determinants with row operations, which is kind of interesting. We have a theorem that corresponds to this. Remember that all matrices are row equivalent to some row echelon form, right? And so if we have an n by n matrix and let R be the number of interchanges, to produce the row echelon form of A. Suppose R is the number of interchanges to produce the row echelon form of A. Then we have that the determinant of A is negative 1 to the R times the determinant of the row echelon form of A. And that's kind of nice. So let's make sure that we understand why it's true before we talk about why it's nice. So R is the number of row interchanges. Every time you interchange rows, you pay the price of a negative, right? So that makes sense. And we know that the only thing left that we need to do is take multiples of one row and add it to another row. And that will not change the determinant. So all that we need to do is compute the determinant of your row echelon form matrix, which is upper triangular, right? And then multiply by the negative 1 to the R term. And that's kind of cool. Why is this nice? How many operations? Suppose you're a computer and you want to compute determinants of large matrices. Suppose you're a computer and you want to compute determinants of large matrices. How many operations are required? If we compute the determinant of a 3 by 3 matrix, if you do it, it turns out that you'll need 6 multiplications, which is 3 factorial. And that's a lot. if the dimension goes up, right? How would we compute the determinant of a 25 by 25 matrix? We would need 25 factorial multiplications, which is impossibly large. So computers cannot compute determinants using cofactor expansion. Instead, row echelon form is a lot easier. Row echelon form is easier because instead we would only need something on the order of 25 squared, multiplications. And that's a lot smaller. So 25 squared versus 25 factorial. So actually computing it with row echelon form is the way that computers like to do determinant computations, which is kind of interesting. All right, let's do one more example to see why our theorem is true. Let's do one more example to see why the theorem is true. Let's compute suppose that the determinant of your favorite matrix, A, B, C, D, E, F, G, H, I, had to do the alphabet, sorry. Suppose that this is -2. Suppose that this determinant is -2. Compute the determinant of your next favorite matrix, G, H, I, D plus 2A, E plus 2B, F plus 2C, A, B, C. Pause the video and see if you can figure this out for yourself. So what has been done to this matrix? I see that I have swapped the first rows. So it's going to pay the price of a negative, right? So I've interchanged rows. So we've done one interchange. And we took a multiple of one row and added it to another one, which does nothing for us, right? So the only thing that I need to account for is this one interchange, because this doesn't do anything. So I have 2. Yeah? I'm going to leave you with a question. Be a good quiz or test question, don't you think? True or false? Is it true that the determinant, suppose A and B are both n by n or whatever, is it true that the determinant of A plus B is equal to the determinant of A plus the determinant of B? And I'll leave you that question. Thanks so much, guys. I hope that this helps. If you have any questions, feel free to send me an email, and I'm happy to help via email, or we can set up a time to video chat in Zoom or whatever. So thanks so much. Have a great day, and I'll see you in the next video.